Neutrinos play an important role in atomic nuclei. They appear as byproducts in one of the most common nuclear processes encountered in nature, beta decay. They're also special in that they may explain why the cosmos that formed in the Big Bang was not annihilated by equal parts antimatter, but instead resulted in a universe dominated by matter. Einstein pointed out that energy can convert to mass by simultaneously creating particles and antiparticles. Conversely, a particle can meet its own antiparticle and they annihilate and convert to energy. In 1937, Ettore Majorana demonstrated that all results of beta decay theory remain unchanged if the neutrino were its own antiparticle. But can a particle also be its own antiparticle? Yes, for example, this is true for a photon. But what about neutrinos? If a neutrino is its own antiparticle, then two neutrinos can annihilate each other. In the double beta decay process, both antineutrinos are created with the same helical spin direction. However, if the neutrinos have a non-zero mass, there's a tiny possibility for a different helical direction, and then this neutrino can be reabsorbed in a double beta decay process. No neutrinos appear. This trick is called neutrinoless double beta decay. This quantum sleight of hand has produced two electrons with nothing else to balance the decays. This violates an assumed truth in nature, that one cannot create electrons without associated antiparticles. So this would be shocking. Since there are no more neutrinos to carry away the energy, the sum of the electron energies must become unity due to the conservation of energy. The telltale signature would thus be a small increase in probability at unit energy. The probability for this is very, very tiny. Why is this so? The best-known upper limit of neutrino mass is less than 1/millionth of that of an electron, as extracted from precise measurements of the energy spectrum of tritium beta decay. Neutrinos can only change their spin because of this mass. Now that their mass is so tiny, it reduces an already rare double beta decay process even more. In a nucleus, the neutrinoless double beta decay process may only happen once every 10 to the power of 26 years, dwarfing the 14 billion year age of the universe itself. For each ton of material, scientists look for one decay event per year. Ton-scale experiments are envisioned requiring vast amounts of designer nuclei in order to observe a single double beta decay event. If neutrinoless double beta decay can create electrons without antiparticles, it points to a mechanism that creates matter but not antimatter. This could lead to a deeper understanding of how our universe exists in the first place. Scientists have assumed that equal amounts of matter and antimatter were created after the Big Bang, which would have annihilated each other, leaving a universe empty of matter and filled only with energy. But clearly our universe is made of matter, with no sign of a parallel antimatter universe. Why we survive the annihilation is a cosmological mystery. Can the observation of neutrinoless double beta decay point to an explanation of the matter-antimatter asymmetry that we see in our cosmos?